We have been asked to prove that 1 minus cosine 2 theta is identical to tan theta sine 2 theta, where theta isn't an odd multiple of pi over 2 and where n is an integer, okay? And this question is worth 3 marks. So you have two ways to do this. The first way is you can go from 1 minus cosine 2 theta to tan theta sine 2 theta, so that's the first way. Or the other way is you can go from tan theta sine 2 theta to 1 minus cosine 2 theta. Okay, I'm going to choose the latter, so I'm going to go from tan theta to sine 2 theta, just because I think it's easier, okay? And the marks can credits both ways, so don't worry about it. The first thing I'm going to do is I'm going to use the identity that tan theta is identical to sine theta over cosine theta, okay? So what this means is that tan theta sine 2 theta equals sine theta over cosine theta times sine 2 theta, okay? The next thing I'm going to do is I'm going to use the identity that sine 2 theta, okay, is identical to 2 sine theta cosine theta. And what this means is we will get that we have sine theta over cosine theta times 2 times sine theta times cosine theta, okay? From here, the two cosine thetas cancel, so what we are left with is that this equals, okay, 2 sine squared theta, alright? Now, what we need to do is we need to use another trigonometric identity, okay? And that identity tells us that cosine of 2 theta equals 1 minus 2 sine squared theta, okay? What we're going to do is we're going to rearrange this for 2 sine squared theta. So this means that 2 sine squared theta equals 1 minus cosine of 2 theta, and by extent we get that this here equals 1 minus cosine 2 theta as required. So this question is worth 3 marks. Your first mark comes from using that tan theta is identical to sine theta over cosine theta, and that sine 2 theta is identical to 2 sine theta cosine theta, to get this line here, so up until this, okay? Your second and third mark come from doing the simplification of cosine theta to get 2 sine squared theta, and using the fact that cosine 2 theta is 1 minus 2 sine squared theta, rearranging that to complete the proof as required. So this gets you your final 2 marks. We have been told, hence, solve for minus pi over 2 to pi over 2 for x, the equation secant squared x minus 5 times 1 minus cosine 2x equals 3 tan squared x sine 2x. And we are told, give any non-exact answer to 3 decimal places where appropriate for 6 marks. Okay, so first I'm going to highlight the domain over which x is valid for, okay, like this. And I'm also going to highlight that we need to give any non-exact answers to 3 decimal places, okay? So what we need to do is we need to look at the equation we've been given and try and manipulate it using this identity that we worked out in part A, okay? So the first thing we're going to do is I'm actually going to take tan squared sine 2x and I'm going to split it up. So I'm going to say that secant squared x minus 5 times 1 minus cosine of 2x equals 3 tan x times, and then we have tan x sine 2x, like that, okay? Now what we can do is we can use our identity, so I'm just going to show that we're plugging this into here, okay? So what we would end up with is secant squared x minus 5 times 1 minus cosine of 2x equals 3 tan x, and then 1 minus cosine 2x. 1 minus cosine 2x. Like that. Okay? The next step I'm going to do is I am going to bring both sides, the right hand side over to the left, okay? So what we'll end up with is secant squared x minus 5 times 1 minus cosine 2x minus 3 tan x 1 minus cosine 2x equals 0. What I'm then going to do is I'm going to take out 1 minus cosine 2x out as a factor, okay? So we will end up with 1 minus cosine 2x and then times secant squared x minus 5 and then minus 3 tan x. Okay, just put the square bracket equals 0. Okay, so just in conclusion, what I've done is I've taken 3 tan x times 1 minus cosine 2x, moved it to the other side, and then taken 1 minus cosine 2x out as a factor to leave secant squared x minus 5 minus 3 tan x. Okay. Now, what I'm going to do here is I'm going to introduce another step, and I'm going to use the identity that secant squared x equals 1 plus tan squared x. Okay, and the reason I'm going to use this is because we are going to say that using this we get that secant squared x minus 5 equals, so it's going to be tan squared x plus 1 minus 5, so this is going to be tan squared x minus 4. Okay, so tan squared x minus 4. I'm going to plug this for our secant squared minus 5. So what we will end up with is 1 minus cosine 2x times, let's just fix the bracket sign, times, so we've got tan squared x minus 4 and then minus 3 tan x, okay, equals 0. Alright, now at this point we have two products which equal 0, which means either 1 minus cosine 2x is 0 or tan squared x minus 4 minus 3 tan x equals 0. Okay, so let's write this down. What we can say is 1 minus cosine 2x equals 0, cosine 2x equals 1. This means that 2x equals the inverse cosine of 1, which is 0, and therefore x equals 0. Now, before we can say x equals 0 and move on, we need to check if it's a valid solution, okay? So, our question said, solve for x between minus pi over 2 to pi over 2. 0 is between there, okay? So this is valid. So I'm just going to write in brackets here, valid, okay? The next step is to solve when tan squared x minus 3 tan x minus 4 equals 0. And the reason I've written it like this is because this is actually a quadratic in terms of tan x, okay? What we can do is we can do a substitution and say let lambda equal tan x. So this becomes lambda squared minus 3 lambda minus 4 equals 0. And the reason I've done this is because now it's in a more familiar form, okay? So usually you're dealing with x squared minus something in terms of x plus a constant. Here we've just substituted lambda, but still you can see the resemblance, okay? It's much more comfortable to work with than just in terms of tan x, okay? From here, what I'm going to say is that we have lambda minus 4 and lambda plus 1, okay? Just checking, minus 4 times 1 gets us minus 4, so that's good. And then minus 4 plus 1 gets us minus 3, so that's good. So this equals 0. And then this means that lambda equals 4, or lambda equals minus 1. From here, because we know that lambda equals tan x, we can say therefore tan x equals 4, or tan x equals minus 1. When tan x equals 4, this means that x equals the inverse tan of 4, and the inverse tan of 4, if you put it into your calculator, you would get 1.3258, etc. And then the inverse tan of minus 1 is minus pi over 4, okay? So minus pi over 4 like that, okay? Again, like we did with x equals 0, we need to check that our x values are valid. So 1.3258 is it in between minus pi over 2 and pi over 2? Well, if you check what pi over 2 is, you will see that it is. So this one is also valid. Okay, and minus pi over 4 is again in between there, so this is also valid. Okay, so now what we need to say is solutions are x equals 0. Now remember, for x equals 1.3258, because it's not an exact value, we were told to round it to 3 decimal places. Okay, and that is exactly what we're going to do. We're going to say this rounds to x equals 1.326, and then finally we have x equals minus pi over 4. Okay, so that is 3 solutions for our equation. So this question is worth 6 marks. Your first mark comes from doing the work to get that x equals 0 as the first solution. Your second mark comes from using secant squared x equals 1 plus tan squared x, substituting that for secant squared x minus 5, and by extent getting that this here equals 0, so 1 minus cosine 2x times tan squared x minus 4 minus 3 tan x, so that. Your third mark comes from knowing that tan squared x minus 3 tan x minus 4 equals 0. Your fourth mark comes from factorizing tan x correctly, so getting tan x or lambda, either way, equals 4, and it equals minus 1, so this will get us here our fourth mark. And then our fifth and sixth mark come from getting the final 2 correct solutions, so this will be 1.326 and x equals minus pi over 4.